The problem of producing computer intelligence is analogous to the age-old debate in education between teaching discipline and the skills that follow from direction versus fostering critical thinking and the skills that follow from creativity. While human beings can do both reasonably well, computers seem to be only able to follow directions, albeit in an exceptionally fast and accurate way when compared to humans. Presently, there is wide agreement that it is the integration of neural networks dedicated to specific types of processing that produce the advanced cognitive capabilities that we see in humans. This approach is further supported by advances in the field of machine learning. The advent of artificial neural networks has led to the solution to several computational problems that were once considered intractable, like image identification, speech recognition. Historically, computational learning models have been limited by their linear nature, a technical lack of storage, and limited networking capability. The idea of programming software that uses networks of distributed information to solve problems, however, actually can be traced back to the earliest investigations into machine learning. This line of inquiry came to be seen as an investigational dead end due to the limits of computation. Even to make simple computational judgments can require access to massive networks of information that seem to border on the infinite. However, in the last 20 years, we have seen an exponential improvement in computational processing hardware and storage capacity. As computer hardware has improved, so has the possibility of programming large, expansive neural networks capable of accurate problem solving. The first researchers to demonstrate the power of computational neural networks did so by using a graphic processing unit to train a computational neural network with 5 convolutional layers and 60 million parameters on a set of 1.3 million images. Since this time, the use of convolutional neural networks has become standard in most operational searches, particularly in deep learning and data mining programs that can detect subtle differences and patterns in large data sets because of their many convolutional layers of processing. The power of convolutional neural networks is that they require relatively minimal processing to produce results. Historically, it was believed that for computers to solve even rudimentary problems, all aspects of that problem would need to be hand-engineered, meaning that the programmer would need to consider every possible input into a system and pre-program each of these possibilities into a coded solution. The problem of this computational approach is on display in early adventure-style computer games like Colossal Cave, where a player can interact with an expansive textual computer environment. However, gameplay was confounded by the non-exact nature of human communication. Humans can express ideas using seemingly infinite possible collections of words that are configured in all different kinds of ways, whereas computers are limited only to their pre-programmed considerations. Due to this computational limitation, much of the play in these kinds of early computer games revolved around the player trying to decipher which words or phrases the program could actually even understand. This was because each entered response needed to exactly match the programmer's pre-programmed list of expected responses. If you're unsure of what I'm trying to explain here, please go to the linked website and spend 5 or 10 minutes playing Colossal Cave Adventure. I am sure you will quickly realize the limitations of this style of programming for yourself as you find yourself spending an inordinate amount of time trying to figure out which text commands the computer will actually accept. But it does demonstrate a raw and basic barrier between human and computer intelligence.